Now, what we are talking about here is the process, and this is where some of the confusion arises. The process of converting these feedstocks, which you see on your left-hand side, to a product, polyethylene or polypropylene or PLA, is the process. What is the impact of the environment on the carbon? But what I am saying to you is that the value proposition is not arising from the process. We absolutely have to do and continue to improve the process, but you have already an intrinsic value proposition coming from these carbons. You see that on your screen. These carbons arise from the feedstock selection, petro versus bio. So this carbon could be petro or it could be bio. And what we are saying is that by switching this carbon to bio, we have a reduced carbon footprint. And I will illustrate that in my next slide. All right? So this is also another polymer you have heard a lot about, PET, the bottles, and you have heard from the Coca-Cola's, the plant bottle. So the question here is, you can look at it, there is 10 carbons, asking the question, do I have to replace all 10 carbons, or if I replace only 2 carbons, is there value to it? Okay, so keep this in mind as we go to the next slide. And this is the basics. If you understand this, then this is where the message is coming from. You understand from high school chemistry or biology, carbon in the atmosphere is fixed by photosynthesis using sunlight energy to organic carbon. This is your biomass, ag, forestry. I call this new carbon. And here's the key. The rate and time scales of this carbon fixation to new carbon takes place in 1 year if you plant another crop, 10 years or more if you plant trees or grow trees. Now, this carbon over millions of years is converted to fossil carbon. I call this old carbon. So, fossil carbon is also natural. Fossil carbon is also part of the same carbon cycle. And oh, by the way, it is also renewable, okay, or millions of years, but it is renewable. So the issue is not about natural or artificial or synthetic. The issue is got to do with these time scales, 1 to 10 years, millions of years. So what is the problem? The problem is very simple. The rate and time scale of fixing or sequestering carbon to biomass plants is in 1 to 10 years. The rate at which we use it and put it back into the environment around 1, 10, 20 years. But by using fossil carbon, the rate and time scales is in millions of years. We use it and put it back in decades. So it's very simple math. This is not sustainable. So we are sequestering carbon which is present for millions of years. We're using it and put it back. And therefore, what we are submitting is that if you use biomass feedstocks, then you are going to be carbon neutral. So the selection, the origin of the carbon is a good value proposition. And this, ladies and gentlemen, is the fundamental driver for switching feedstocks, which will allow us to move in the right direction. Okay, so, and this slide is illustrating what I just explained to you, okay? Carbon is distributed in different environmental compartments. So right on the top, 730 gigatons of carbon in the atmosphere. In the oceans, 38,000 gigatons. In vegetation, 2,000 gigatons. Okay? Even the fluxes or nature's cycling of the carbon between these environmental compartments is the same, equal. 119 gigatons to the atmosphere, 120 fixed. 88 gigatons, 90 gigatons being sequestered by the oceans. Even farming, changing land use, 1.7 gigatons, 1.9 gigatons fixed. So what is the problem here? You see that on the extreme right-hand column. 6.3 gigatons of carbon going into the atmosphere. There is no corresponding sequestration, fixation coming back in. So the fundamental value proposition is very simple. If we use biomass feedstocks and maintain this natural balance of flux change, that is carbon sequestered versus carbon release, then you're in balance. And this is the value proposition for the switch from petro-fossil feedstock to a bio-renewable feedstock. And so I want to illustrate this with just this slide, just give you a number associated, right? Let us ask the question, if I want to make 100 kilograms of polyethylene, all right, and make 100 kilograms of biopolyethylene, or 100 kilograms of bio-PLA, polylactic acid. You see all those carbons seeing there? That carbon can come from petro, or it can come from bio. And in the case of PET, that carbon can come from bio and petro. So you see the greens there. So the question we are asking is, what is the impact of the switch? And I want to illustrate this with actual numbers. So let's go to the next slide. And this is a little complex, so let me walk you through it. 100 kilograms of polyethylene resin we want to manufacture. 100 kilograms of polyethylene resin contains 85.7 kilograms of carbon. All right? Carbon is then eventually goes to CO2. C plus O2 gives you CO2. So every time there is a manufacture of 100 kilograms of carbon, when this is eventually released into the environmental, there is 314 kgs of CO2 emissions which is released. You see that green thing, 314 kgs. If it is PET, it's 240 kgs. Now, if I switch this carbon to bio, say making polyethylene, making these carbons bio, I'll still put out 314 kgs of CO2. But I plant another crop in the next season or within 5-10 years, if it is a tree plantation, to fix that carbon back into plants. I take 314 out of the equation and I have a zero carbon footprint. This is the zero carbon material footprint coming from bio-PE, PET, and PLA. All right. So very simple. By switching our feedstock, we immediately give an advantage of reducing our material carbon footprint, and that is the value proposition for the bio-based plastics. Okay. So I'll skip this slide because of time and go to the next one. So here are some examples, and I'm sure you're in Rio and this is in Brazil. So Braskem is now manufacturing 250 kilotons of biopolyethylene. They go from sugarcane to ethanol to ethylene, and immediately, as you know, for every 100 kilograms of biopolyethylene, they save 314 kgs of CO2. Of course, there will be additional CO2 savings if the process of converting this sugarcane to polyethylene is also sustainable and done right. And you can see that that is their goal in the whole process. But fundamentally, that's the value proposition. Here is another example, okay? You have heard of Coca-Cola's plant bottle. Plant bottle is made out of the polymer which is shown here. It is called PET. PET is composed of 10 carbons. There is 8 carbons here and 2 carbons there. Today, that PET is made in the following way. They take oil, coal, natural gas, whatever you pick, make ethylene glycol, one component, terephthalic second component, combine it to give you this. Now, all the Coca-Cola plant bottle is coming from a component where taking plant feedstocks, they can go through sugar, ethanol, ethylene to ethylene glycol. So, 2 of these ethylene carbons are coming from plant feedstocks, which means the CO2 evolving out of these 2 carbons is going to be fixed by the next crop or tree plantation is made. In other words, this will have a net zero impact. So take it further. That means out of 10 carbons, right here. 2 is neutral, 8 will contribute to CO2. So what is the value of this in terms of a plant bottle concept? So here's what it comes to. 37.5 million metric tons of PET is used to make bottles for water, for these soft drinks, so on and so forth. If I replace 2 of these 10 carbons with bio, remember that CO2 is then fixed by the next crop, it results in 17 million metric tons CO2 savings, which results in 40 million barrels of oil per year savings. It's not going to solve your world's problem for you, but it is a step in the right direction. And that is the value of switching to a bio-based feedstock, all right?
Ramani, can we wrap up, because I have 3 CEOs here on stage who are waiting to show their products, and I think we're going to run out of time. Thank you. Just take another slide to wrap it up. Thank you.
So this would be my last slide. So I talked to you about the value of bio-based. I wanted to talk to you the end of life. If you do not have an end of life, then you have a problem. So if you have a bio-based plastics, then you need to do recoveries by recycling. So for example, mechanical or chemical. Or you can design for biodegradability. Now, if you talk biodegradable, you must define the disposal environment and time. So composting or anaerobic digestion or marine or soil. The key phrase here is time. If you don't define time and disposal environment, then you have a very vague saying, my product is biodegradable, and that's where all the misleading and deceptive claims are coming from, and you need to be aware of it. There are products like PLA and other polyesters which would meet this requirement, and there are standards, and you need to be aware of that. So thank you for listening, and I appreciate the opportunity.
Thank you very much, Professor Narayan.